The next. So the next speaker is Arjada, who is an assistant professor at the economics department.
Thank you. Thanks to the organizers for putting together this excellent workshop and for including the paper in the program. So this talk will build upon some of the ideas that we saw on Monday morning in the very first session of the workshop. And he talked about dynamic sampling of attributes. Steve and John talked about the Brownian motion as a way of modeling correlation across alternatives in search or across actions in cheap talk. What I'll do here is to come back to the attributes problem, think about static learning in the attributes problem, and model correlation across attributes using Gaussian, a large class of Gaussian processes. And of course, the Brownian motion is among the most well-studied of that class. So to make things precise, let me go over the attributes problem that I have in mind. There's a principal and an agent who evaluate a project of uncertain value. And the value of that project is determined by a mass of attributes. The realizations of these attributes are correlated. And just to be very precise, the value of the project consists of a weighted sum of these attribute realizations. Now, the principal and the agent understand the correlation across attributes, but they disagree on the weights that they put on different attributes. And they will be learning about some of these attribute realizations before making a decision. That learning process will be constrained in two ways. So first, there will be limited opportunities to learn. So the principal and the agent cannot learn all of the attributes, so they'll be confined just to a sample size. And secondly, there will be separation of authorities on who makes the decision and who samples. In particular, in this model, the agent is the one who samples and the principal is the one who makes that decision. The question that I ask is the basic question: which attributes are optimally sampled? How can we think of the optimal sample as varying with the correlation structure across attributes? Now, before I move forward, I want to note here that in this problem, attributes have sort of a dual function. On the one hand, attributes are components that go into the making of the value of the project. So they're sort of payoff relevant. On the other hand, attributes constrain the way that you learn about the project. So attributes also serve as signals about the project. Now, the origins of the attribute problem cannot sort of, the importance of the attribute problem cannot be overstated in the economics literature. It goes back to Lancaster's characteristic-based demand theory and Kinney and Raifa's sort of multiple criteria decision problems. For the purpose of this talk, I want you to sort of keep in the back of your mind that these two applications. So first, we can think of consumers' willingness to pay for a complex product that is made up of different attributes. There is a large literature in consumer research that has shown that consumers do think about correlation across attributes when they evaluate and make purchase decisions. And in particular, Mason and Beckett have sort of this language of the perceptual map of correlations across pairs of attributes. In much of these purchase decisions, the consumers are not deciding, are confined in what they can learn about these products. Their learning of attributes is confined by trial products or nutrition labels, which give information only about certain attributes of the products. So there is some interplay there between the information that's provided and the purchase decisions. Yes. So I want you to think, for instance, of a health authority that is designing the content of these nutrition labels. You could also think about household purchase decisions, collective decisions, and sort of the learning and the purchase decisions being made by different members of the household. So I'm being a bit sort of silent on exactly who is the second player there. Thanks. A second interpretation of the attributes problem goes back to applications in spatial applications of evaluation of the effects of a program, of social program across different sites. We can think of the effect that a program has on sites as attributes and attribute realizations respectively. Pilot studies, the way through which we often learn about the effects of different social programs, can be thought of as this sampling process. There is, and coming back to the question of who is the agent and who is the principal, we can think of the principal as the government that decides whether to scale up these programs, and the agent as either NGOs or federal agencies that decide where to place these pilots, which sites to try as pilots before making this. So what does this paper really do? Well, it does mostly two things. First, it offers a general framework of thinking about attribute correlation. Now, the picture that I want you to keep in mind is the following. So I want you to think of attributes on the x-axis and realizations on the y-axis. Attribute realizations are correlated, and we can model flexibly that correlation by thinking of families of mappings from attributes to realizations. I'll put some structure and discipline the family of mappings that we look at, and in particular, the attribute mappings will be coming from a class of Gaussian sample paths. The primitive in this class will be a similarity measure over different pairs of attributes. And I will be talking quite a bit about the key property that leads to local extrapolation across attributes that I refer to as the nearest attribute property. And then once we understand this framework, then I'll take this framework to attribute correlation structure and how that informs strategic sampling. So I'll start addressing the question of persuasion. In today's talk, in the paper, I address a number of sort of features of optimal sampling, the possibility of inference reversals, the value of sampling irrelevant attributes, whether you want to sample common attributes or idiosyncratic attributes. I'll say a few things about them, but mostly I'll be focusing on the value of sampling irrelevant attributes. Okay. Let me see if there are any questions before I go to the framework. Okay, so two players, principal and an agent, evaluate a multi-attribute project of unknown value. And as I said, the agent is sampling, the principal is making the decision. There's an attribute space. I'll use the notation f of a to denote the realization of attribute a. The value for the project is the sum of all attribute realizations weighted by a weight function that's given by omega, and omega here is indexed by I, because I want to keep track of the player that different players have different weight functions. We'll put some regularity condition on this weight. They're not important for today. You might want to think of either the attribute matters or it doesn't, so weight either 0 or 1. The principal is making a decision that I'll parameterize through this utility function. So this is just quadratic loss over the distance between the decision and the value of the project. So the principal and the agent want this decision to be as close to their estimate of the value of the project. Okay, so prior to the principal deciding on the decision, the agent is constrained to sample at most k attributes at 0 cost. If A is sampled, then its realization is observed perfectly, and I'll keep the two players symmetrically informed throughout the game. Some more language. So an attribute is desirable for player I if the weight is strictly positive, undesirable otherwise. If the weight is 0, I'll say that the attribute is irrelevant for that player. Otherwise, the attribute is relevant. Of particular interest, especially to this talk, is this structure of intervals of attributes that are relevant. So I'll be thinking of intervals of attributes that are relevant for the principal and the agent. The overlap of the two are common attributes, and the rest of the attributes in these intervals will be idiosyncratic attributes. I'll come back to this later in the talk. Yes.
Yeah, so this capital A is an interval, or it can be.
Well, this is just a special case, right? So, but in the general model, we might want to think of it as not necessarily
Even a finite set.
Even a finite set would be fine. Yeah.
What is something?
So I'm getting to that. case, they will be common knowledge. So coming back to the question about attributes, right? So the attribute space lives in RD. For today, I'll think of just single dimensional attribute space. And in particular, we'll talk more about interval supports of these wave functions. Now, let me tell you about the correlation structure. So attribute realizations are determined by an unknown mapping that maps attributes to realizations. And this mapping is drawn from the space of sample paths of a known Gaussian process. The Gaussian process is pinned down by a mean function and the covariance function. The mean function takes attributes to the expected realization. The covariance function takes any two attributes to R. Okay, so it gives us, so basically, this is the mathematical analog of what I just said. I'll assume that the pair mu and sigma are known to both the principal and the agent. And they, of course, because we're within the class of Gaussian processes here, they fully describe the prior uncertainty about the project. We can think, or we can map sigma into a similarity metric across pairs of attributes. I won't talk much about that today, but it's in the paper. This class is rather flexible, the class that I'm considering. I will put continuity of sample paths because arguably we want to think of attributes that are close in the attribute space, have almost the same realization. So I'll just impose that almost any realization of F is continuous. And it's without loss in this environment to normalize the variance of any attribute to be either 0 or 1 and to load all the rest into the covariances. So let's come back to the Brownian here. So the Brownian motion is perhaps the most well-known of Gaussian processes. So let's map the elements that I told you about. So we've got attributes in 0, 1 in the x-axis and realizations on the y-axis. The Brownian motion is parameterized by a linear drift. So the expected realization of each attribute is A/2 in this example, and the covariance is the minimum between two attributes. Yes.
Measure on script A?
Say that again, please.
Is there a measure defined on script A? I might have missed it.
So you can think of the weight function as a measure.
But I thought the weight was a function of OS.
You can think of omega as a measure. And of course, in the probabilistic sense, there's a measure over.
But I thought omega is I see what you're saying. Okay.
So let's come back to the Brownian and perhaps illustrate the rest. So here I can think of the weights, all attributes in 0, 1 being weighted by weight 1. So that's a measure. Sure. And I'll come back to this picture when I talk about the value of the project.
So I should just think of the measure on A as being uniform.
You can, but I'll come back to weights and sort of introduce conflict between these weights. But for now, you can.
I think when you said sample A, you meant pick A, but then sample F.
Yes. So coming back to the sampling question.
Oh,
so
okay.
When you pick a sample, so any sample of attributes gives us the realizations of these attributes in the mapping F. So so coming back to the question about what is a sample here, what does it mean to sample? It means that we observe this vector of F of realizations of attributes, and of course that's jointly Gaussian with some mean and some covariance matrix that's determined by our primitives. Without loss, restrict attention to non-redundant samples. This covariance is non-singular. Now the prior value from the project, yes.
To also be positive semi-definite covariance for it to be a valid Gaussian process.
Yeah, correct. Yes, and across all samples. Yeah. The prior value from the project is determined by the prior mean mu. The prior distribution of the value is, of course, Gaussian with this prior value mu 0 for player I, and a notion of aggregate uncertainty that, of course, depends on sigma. So you can think of this as the aggregate uncertainty about the project for player I. the status quo, in the absence of any information, the principal just takes a decision that's equal to their prior value, and this is the loss that's incurred. Okay, so coming back to the Brownian motion, the prior value, so weights are equal to 1 for all attributes. The player in this figure wants to estimate the area under the sample path that's being realized, but of course under the prior, which is the linear drift, they estimate the yellow area based on the red area, so the triangle determined by the prior mean. Okay, so let me say a couple of words here on the literature, and in particular, I want to emphasize this line of work that in economics is using Gaussian processes to model correlation across attributes, and Steve has done much of the work in this line of work in finding and identifying and showing the power of the Brownian motion across different applications. More recently, there is work that is sort of starting to look at different Gaussian processes as sort of alternative ways that might fit different applications. And so we're starting to open the box of different Gaussian processes as well. Because of the crowd that I'm that I'm in front of, I want to mention the line of work that starts with spatial statistics and lately has been taken up by machine learning that looks at Gaussian processes very much in the same way that I'm using them here. Several of the tools that I'm leveraging here are coming from work, for instance, by Rasmussen and Williams. They have a very nice textbook on Gaussian processes. In the attribute problem, I want to argue the flexibility of the correlation structure is key, because I want you to think of the correlation across attributes as capturing something intrinsic about the nature of the project that you're evaluating. So I would argue that in the attribute problem, it's particularly important to think about a large class of correlation structures. Okay, so if there are no questions, then I want to go to the basics, extrapolation, and identify a particular property across this large class of correlation structures.
Budget constraint?
Yes, thank you. So there is, you can sample up to k attributes at no cost, and the cost becomes infinite attributes.
Right, I just missed this. You know the weights.
You know the weights. So the principal, so both of them know the weights of each other as well as theirs. They also know mu and sigma. So there's common knowledge in all of these. Okay, so given a sample and the realizations observed by that sample, players will extrapolate to the rest of the attribute space. And I'm showing here 4 different Gaussian processes and how extrapolation goes for those. So in particular, let's look at the Brownian here in figure A. So the Brownian is just linear extrapolation across the data points that we've observed. And typically we refer to the extrapolation across any 2 known points as the Brownian bridge. Okay? Now, very much in that same way, we can extrapolate across another process, the Ornstein-Wiedenbeck process, which I'll be talking quite a bit about, and I'll show that extrapolation is simple for that process in a well-defined sense. Or we can go to fancier processes like the squared exponential, which I'll also talk about, or the polynomial, which I won't talk much about, but I sort of still want to show the richness of extrapolation. Now, fancy as this looks, this is actually just Gaussian updating. So from once I look at the attribute realizations that I've observed, I extrapolate to the rest of the attribute space. I have an estimate for f of Äîthat for any other Äîthat, and then I aggregate all of that into an estimate for the value of the project. Okay? So given a sample and the realizations, the posterior expected value is just the linear combinations of the sample realizations. What is key here is understanding the weights that I put on these realizations. So I'm extrapolating outside of the sample. So I put a weight. If I'm extrapolating to attribute Äîthat, I weigh the different sample attributes in a particular way. And then the weight that I put on the jth attribute in the sample, or rather the weight that player I puts on the jth attribute in the sample, aggregates the weights that they would put when extrapolating to each individual attribute outside of the sample. There is a standard Gaussian updating gives us these weights. What I want to point out here is that understanding the nature of these taus is essential, and that is determined by the covariance sigma. And in principle, we can observe, so I'll point out two different notions of inference reversal in this environment. The first one is just the idea that you can have a sample weight that has a different sign from the sign that you put on the attribute weight. So omega and tau need not have the same weight. Okay? So you can have desirable attributes that get a negative sample weight in the sample. Now, let's consider the following property on these processes. So let me think about processes in which only the closest attribute that I've observed is useful for extrapolating to a given attribute outside of the sample. So in particular, in the depiction up here, so I can think of this entire space of attributes, but to the left of A1, only the realization of A1 is relevant. Between any two attributes, for any attribute between A1 and A2, only the realizations of A1 and A2 are relevant, and so on. I refer to this as the nearest attribute property. This captures, in a sense, out of sample extrapolation that is local. Okay, or another way to say this is that the sample will divide the attribute space into components or clusters of attributes that are conditionally independent when conditioning on these values. Captures a notion of sort of the project can be broken down into conditionally independent components. Now, what types of processes will give me this pattern of extrapolation? We'll say that extrapolation to out of sample attributes satisfies the nearest attribute property if and only if the attribute mapping F is Markov, if and only if, when translated in the language of the covariance function, the covariance satisfies this property. And I want to remind you here that I've normalized the covariance, the variance of each attribute to be either 0 or 1 without loss. Okay? So what this tells you is that when you you look at three attributes ordered in this attribute space, the correlation between attribute A and A double prime is just the correlation between attribute A and A prime times the correlation between attribute A prime and A double prime. So once we take this into account, then we can show that the sample weights take a very simple form. For instance, the sample weight of the first attribute here aggregates the correlation of that attribute with any other attribute to the left of A1. Because A1 is the only attribute that's relevant for those attributes to the left, we take sigma to be the entire correlation here. Whereas for attributes between A1 and A2, both attributes A1 and A2 are relevant. So we prorate the correlation between that attribute and A1 by how close that attribute is to A1. So there is a very simple structure that gives these sample weights. Now, I want to explore the implications of this property for how strategic sampling looks like. And in order to do that, I picked two, sort of as illustrative examples, two types of covariances, one of which violates the nearest attribute property and the other one which satisfies the nearest attribute property. And I will work with covariances that have a very simple interpretation, a distance-based interpretation. Attributes that are closer in the space are more strongly correlated. Now, the Ornstein-Uhlenbeck covariance, which is given by this first exponential form here, satisfies the nearest attribute property because the Ornstein-Uhlenbeck process is Markov. The squared exponential covariance, which is also an exponential, takes an exponential form that's slightly different from the Ornstein-Uhlenbeck one, in fact, violates the nearest attribute property. It's a non-Markov process. Both of these covariances have very similar forms, yet we'll see that the implications for strategic sampling are rather different. Covariances that look like this have been explored in the literature, both in the psychology literature, but also in economics. We've axiomatized exponential decay as a similarity function. So that's to say these types of correlation structures are somewhat familiar to us. Yes.
the covariance kernel is rank 2? Or
I'm not sure what you mean by rank 2. So let's talk more about that. Okay, so first let's start from the benchmark in which both the principal and the agent have the same weight function. So essentially there is a single player. From what Annie told us on Monday, we know that this is a relatively simple problem for Gaussian for Gaussian structures. So we can rank samples of attributes in terms of the informativeness that the variance of the distributions that they induce on posterior values. And we want to maximize that informativeness. So we want to pick samples that have the highest posterior variance. In this environment, we can go one step further. We can actually, because sample weights are so important to this argument, we can write the posterior variance in terms of these sample weights. So the optimal sample in this benchmark, which I refer to as the single player sample, maximizes the sum of products of this form, where the first tau here is the sample weight that we assign to the jth attribute in the sample, and the second tau is the sample weight that we would assign to that attribute if that was the only attribute that we observe. Okay, so this is the characterization of the optimal sample in this benchmark. The second form of inference reversal that we can see here is that the optimal sample can feature attributes that, if they were the only attribute that we observe, we would assign, let's say, a positive weight, but when we put them in the context of the sample, we assign them a negative weight. The reason why we tolerate such attributes in the optimal sample is for the value that they generate, the spillovers that they generate for other attributes in the sample due to correlation. In the interest of time, let me just say here that the nearest attribute, once we impose the nearest attribute property on this characterization, we can actually observe that the optimization problem for identifying the single player sample boils down to k local optimization problems. What does that mean? That means that if you tell me A2, the second attribute in the sample, then I only need to know A2 in order to pick the optimal A1. When I look at A2 and A4, those are the only attributes that I need in order to optimize on A3 and so on. So we can break this down into k simple optimization problems. Now, the argument that I'll make for the rest of the time here is that the nearest attribute property limits the value of sampling irrelevant attributes. In the benchmark in which the principal and the agent do not disagree on the weights, this will take the following form. Any single player sample will consist of relevant attributes only. So if there is no conflict between the principal and the agent, they will never sample irrelevant attributes. So this is not due to correlation between attributes. It's not necessarily the case that it's not a trivial statement to say that you never want to sample irrelevant attributes. Remember that irrelevant attributes are attributes for which you assign 0 weight. However, knowing an attribute tells you things about other attributes. So conceivably, we can think of structures in which it might be optimal to sample irrelevant attributes for the informational spillovers. However, when the covariance structure satisfies the nearest attribute property, it's strictly beneficial to sample relevant attributes. And I invite you here, just sort of, I'll make a heuristic argument for why this is the case. So let's suppose that we've got 2 intervals of relevant attributes, and I want to think about the value of sampling attributes outside of these 2 red intervals. Okay? First, let's think about sampling attributes to the left here, so attribute A1. Okay? So shifting A1 closer to the support of the weight functions improves posterior variance because it gives you more information about both intervals that are relevant to you. Now, there's an argument to be made here because the weight that you put on that first attribute and the weight that you put on that, both in the context of it being in the sample and if that were the only attribute that you observe, will increase. whereas the weight of the second attribute will decrease. So you still have to show that the different directions boil down to posterior variance going up. But the intuition is that moving closer to both intervals will increase the informativeness of the sample. Let's think now about perhaps a more intriguing case in which you sample an attribute that's between the two intervals. So in principle, that attribute will give you information about both intervals of interest. Now, if we had two such attributes, then you can see that moving A3 to the left and moving A4 to the left will strictly improve informativeness. And the reason is that those two attributes sort of are each responsible for its own interval, and moving them closer to those intervals will make the sample more informative. If there was only one attribute between these two intervals, then this is less obvious because moving it closer to one interval decreases its informativeness for the other interval. However, these two intervals are independent conditionally on the realization of that attribute, and we can show that the posterior variance is strictly convex in A3. So moving A3 all the way to one interval or the other, depending on the size of these intervals, will be strictly beneficial. Takes an argument to show that this is actually the case for the endpoints here in this sample. So the first and the last attribute, you never want to put them in between the two intervals as well. And the argument is slightly more complex that goes through. So what I've told you is that in this single player world, you never want to sample irrelevant attributes if the nearest attribute property holds. Now, can we think of a world in which you might actually want to do that? That's why we go to the squared exponential covariance. This is the covariance that is distance-based exponential, but violates the nearest attribute properties, not Markov. And I have examples in the paper that sort of show that even in simple cases, such as when you can sample only one attribute, you might want to place that attribute in between these two intervals because that attribute will be informative about these two, both of these intervals, and conditional on the realization of that attribute, these two intervals are not conditionally independent, so we don't have the strict convexity there. Interestingly, that will be the case if correlation is high and the intervals are of comparable size. So in a sense, if they're of comparable size, you're very interested to learn about both of them. So there is high value in sampling an attribute that will tell you something about both of them. And that will be most valuable when the correlation between attributes is high, so you can actually effectively extrapolate even if you're not in either of these intervals. Okay, so I've told you about the single player problem. Now let's go to the strategic problem. Okay, so this is the problem in which the agent and the principal are not aligned in their attribute weights. So what's the inference problem here? So we go from a sample to the principal making a decision. The optimal decision of the principal is just taking a decision equal to their posterior value. And so this is what the agent considers in their expected payoff. So we're looking at the expected value, the expected quadratic loss between the agent's value and the decision that's taken by the principal. Interestingly, this expected loss can be written in terms of two sufficient statistics. How informative is the sample for the principal? So how much variance does the sample induce in the principal's decision? And how much does the sample align the value of the agent with the principal's decision? So we can boil down the sample choice into a bivariate Gaussian distribution between the agent's value and the principal's decision. The sample choice controls how much information you give to the principal, but it also controls how this value, the value of the agent, correlates with the principal's decision. So the statement here, the general statement is that any optimal sample will solve this maximization problem, where alpha 2 let's start with alpha 1. So alpha 1 is the posterior variance for the principal. So this is the variance of the principal's decision, or what we before had as the posterior variance in the single player sample. And alpha 2 is the second sufficient statistic that captures the covariance between the agent's value and the principal's decision. We can write alpha 2 in a similar manner to the posterior variance as a sum of product terms between different sample weights. Notice though that in this case, the weight, the sample weight, the first sample weight is the principal sample weight, and the second sample weight is the agent sample weight. So this is a term that's capturing the covariance between the agent and the principal. So the agent is essentially balancing two considerations: aligning the principal's decision with his value. So the agent prefers higher alpha 2, while also giving as little information as possible to the principal, so keeping alpha 1 low. And the extent to which the agent can do both is, of course, constrained by the correlation structure across attributes. Now, in this decision problem, the trade-off between alpha 1 and alpha 2 is, first of all, linear, and secondly, it's independent of prior values. So this is a problem that we can handle in understanding the form of the optimal sample. The optimal sample will consist of attributes that induce positive covariance between the principal and the agent. This should be obvious. If you pick a sample that induces negative covariance, you're likely to move the principal in the opposite direction to the direction that you want them to move. And secondly, it's without loss to consider samples that for which both players put non-zero weights. Okay, how much time do I have? I think we go until
7 and 8 minutes.
Thank you. Now yes.
Sorry, I'm familiar with the model. I just want to understand the strategic part of it. So the agent chooses the K points.
Yes.
According to, they want to optimize their value, but the decision, the principal then makes a decision based on the observations. And the utility of the both the players is this squared the decision minus the value.
Correct. Yes. Okay. So, and essentially these two sufficient statistics are capturing first the covariance between the agent's value and the decision of the principal, and secondly, the variance of that decision.
It's going to throw the ball at one time with a force.
Start with sampling on. Yes. I want to note though here that because of the structure of the decision problem, the sampling does not depend on the evolution of posterior values. So dynamic learning is very much similar for this problem. Yes.
So does it follow from some generalization that the principal needs to make its decision the way it was written here?
Does it follow
from generalization that the principal's decision has to be the way it was written here? It seems to me that like the principal just takes at face value the observations.
Yes, so I hear a couple of things there. So first, because this is quadratic loss, right? Decisions are continuous and just equal the estimate of the value for the principal. I'm taking it as an assumption that it's rather a commitment assumption that once an attribute is sampled, its realization is observed by both the principal and the agents. I think
The agent cannot help it.
Correct. Yes.
So it's not the more general setting where
it's not a disclosure model or a cheap-up model like the one that we saw. It's simply a strategic sort of sampling model with commitment on what you show. Yeah.
Decision given the attributes, will it pay for the principal to say the attribute selection by saying this decision could do this.
Correct. Yes. So this is not a contracting problem in that sense, or sort of the principle here is moving second and making the optimal, the best response decision based on the sample that was observed. We could think about sort of the principle coming first and optimizing over the ways to incentivize the sampling of particular samples. Yeah, but there is commitment in what is shown. So once the attributes are sampled, what are the realizations that are shown? Thank you. Now, this characterization will reduce the k-dimensional sampling problem. You have to pick k attributes into essentially a two-dimensional one. You only need to worry about these two sufficient statistics. Given an attribute correlation structure, the task is to understand the set of possible pairs of alpha 1 and alpha 2 that we can induce, and then choose the best one from that set. So we want to think here about the feasible set of pairs of alpha 1 and alpha 2. The attribute problem is such that the correlation across attributes determines the shape of this set. So in order to be able to understand the shape of this of the optimal sample, we need to put a little bit more structure on the correlation. Now, in the remaining time, I want to make the argument that even in the strategic setting, irrelevant attributes are of limited value. We will see that irrelevant attributes will be sampled sometimes, but they will be sampled minimally in a very precise sense. So does the agent strategically sample irrelevant attributes? The statement is that if sigma satisfies the nearest attribute property and the players have an interval support for the weight functions, doesn't need to be a single interval, could be multiple intervals, then in any optimal sample, two things are true. So first, no attribute is truly irrelevant for both players. So if we see an attribute that is sampled, it must be relevant for some player. And there can be at most two attributes that are irrelevant for some player. So that's to say, if I see an attribute that's being sampled, first, it must be relevant for one of the players. And second, at most two attributes can be of one-sided relevance for only one player. How do we see this? Well, let's start with, I'll do this in 3 steps. So let's start with thinking about, so we've got the agents interval in red and the principles interval in green here. And let's think about sampling A1, which is to the left of the agent's interval in this depiction. Moving A1 closer to the intervals, to the interval of the agent will increase both the informativeness for the principal, because we're moving closer to the principal's interval, but also the covariance between the principal and the agent, because it's the sort of an attribute that moves them closer will align their interests better. So we need to see by how much each of these sufficient statistics is moving in order to determine the trade-off between the two. Now, because of the property on the covariances that I showed you, that essentially is sort of a triangle property across for sigma, we can show that both of these sufficient statistics are actually increasing by the same factor. Because the trade-off between these two sufficient statistics is linear here, that means that moving A1 closer to the intervals of the two players will increase the added value of the sample by this factor as well. Okay. And this factor is positive. Might we want to sample something that's in between the principal and the agent's intervals? Roughly, once I sample something in between, the two intervals become conditionally independent. So the covariance that is induced by any attribute in between the two intervals is effectively the same. So conditionally on sampling between the two intervals, I only need to worry about how much information I'm giving to the principal. But of course, in that case, I'd rather take A1 and move it all the way to the agent's interval in order to reduce the amount of information that I'm giving to the principal. So you never want to sample between the two intervals. And lastly, might we want to sample more than two attributes that are irrelevant for some player? Now, first of all, let's notice here that the principal will never pay attention to more than one attribute that is relevant for the agent only. And that's because all subsequent attributes beyond that do not add any further information if the nearest attribute property holds. But the agent also does not benefit from giving the principal more than two attributes that are relevant for the principal. And the reason is because adding more of these attributes will not affect the covariance. By adding more of these attributes, you're not making alpha 2 greater, but you are adding strictly more information for the principal. Okay, so you never want to sample things like in this non-overlapping case that I have here, when these are irrelevant for the agent and these are irrelevant for the principal. You never want to sample something like A3, because A3 does not affect the covariance between the two players, but is strictly informative for the principal. And we have to make an argument to show this in all the possible configurations of overlapping and non-overlapping intervals. Now, coming back to the example that I've been carrying with me to show that once the nearest attribute property is violated, you might actually see irrelevant attributes being sampled. We go to the squared exponential covariance, and we can show that. So this is just an illustrative example here. We're going to show, so we've got the agent's interval, the principal's interval, and what I have here is the optimal attribute that is sampled as the correlation increases from almost perfect independence to almost perfect correlation. And as you can see here, we sample irrelevant attributes both for low correlation and for high correlation. One sort of interesting fact is that when the attributes are almost independent, the primary concern for the agent is to maximize alignment between the principal and the agent. And that's the reason why we see attributes in here between the two intervals being sampled, because they maximize covariance between the principal and the agent. When the attributes are almost perfectly correlated, the principal just extrapolates too much from the sample. So the primary concern is to minimize the amount of information that we're giving to the principal. And that's the reason why the optimal sample goes as far as possible in the attribute space. Okay, so I think thank you. So I'll just conclude by pointing out a few things that are in the paper that I didn't get to talk about. So in the paper, I look at questions like, might you want to sample idiosyncratic attributes or common attributes? I've told you something about idiosyncratic attributes, but essentially we always sample as few idiosyncratic attributes as possible, and we maximize sampling of common attributes. In the paper, I sort of give a general characterization of sampling both in the single player benchmark and in the strategic benchmark for any K for the Ornstein-Uhlenbeck process. And we can use the Ornstein-Uhlenbeck and the squared exponential process to think about comparative statics in correlation, because both of these covariances have a parameter, the parameter L, that parameterizes how correlated attributes are across a given distance. There is some literature, very interesting literature in consumer research that thinks about inferences that consumers draw across attributes of a product. So I have a discussion there on how the inference reversals and the sampling of irrelevant attributes might have implications for such experiments on product evaluation. And finally, I just want to point out that the framework is tractable to address various applications, both in the attributes problem, but also beyond the attributes problems, in problems of search and others. So hopefully we'll see more work on these alternative correlation structures. Thank you.
So, any question?
I'm still a little confused about the nearest attribute property. So is this different from saying that this is Gauss Markov?
This is indeed equivalent. So let me see whether I can scroll that. Yes, it's Markov.
So it really is a rescaling of the OU process. Like it's sort of up. There's a representation theorem which says any Gauss Markov process is OU up to like a rescale.
Right. I see the connection that you're drawing there, and we can talk more about this offline, but essentially these three properties are equivalent. So for the purpose of what I'm doing here, it is the second way of writing things that is particularly important for me, but you know, the Brownian is also Markov, right? So that's another sort of process we might want to think about, is satisfying this linear subdivision.
Okay, so thanks and see you at 11:15.